Hello. In this subpart of the lecture number 19 of Physics 401A, we discuss the application of regular perturbation theory in the case of ordinary differential equations. Okay. In the first subpart of this lecture, we discussed how to apply the perturbation method in case of algebraic equations, and we considered the case of a very easy quadratic equation, which we know also in the perturbed case how to solve exactly, right? Now here we start also with a very simple equation, and which is basically our target equation. So we, if you remember, we digressed to this method of perturbation from the discussion of small oscillations. So our main or the equation of reference should also be the equation of simple harmonic oscillation. Okay, and we can change this system by adding, change this equation by adding different type of contributions, different type of terms, and to see how the global behavior of the system changes. Okay, but the main equation remains this one: d2y dx2 plus y is equal to 0. Okay, so we just consider one dependent variable y and one independent variable x. Okay, and this is, you can easily recognize, this is nothing but equivalent to d2y dx2 plus omega square y is equal to 0, where omega is exactly equal to 1, right? So for unit angular frequency, the simple harmonic oscillation can be written in terms of the y and x, like d2y dx2 plus y is equal to 0. Okay, so for oscillation you can easily understand x is equal to t or time, and y is the displacement. For some cases this is linear displacement, for some cases this is angular displacement, whatever. Okay, now we want to see how it behaves, how this equation behaves when a small perturbation term, let's say 2 times epsilon times dy dx, is added to the system. Okay, beforehand we also discussed, when we introduce this type of system in general, but not necessarily the coefficient is very, very small. That was the case of damped oscillator, if you really can connect. So dy dx for our physical case would be just nothing but the velocity of the system, and the damping force is usually proportional to the velocity, right? And then this basically gives an unforced damped oscillator, right? Okay, now here we are and actually we showed that we could calculate that as well exactly. So again the same thing, in this special case, special example, we know how to solve both the unperturbed and the perturbed version exactly. That's bonus. But at best, what is our requirement is that we should know the unperturbed equation to solve exactly. Okay, now for the perturbation of, after the perturbation is added to this system, this looks like this, where epsilon should lie between 0 to 1, but always being very, very less than 1, so that this is an effective perturbation parameter or smallness parameter. Once again I write this is 2 times epsilon, that is just for algebraic convenience. Okay, and our initial conditions will be y is at 0 is equal to 0 and y at 1 is equal to 1. Okay, so we give 2 initial conditions. Now if we just say that our x is such a variable which may vary only between 0 and 1, okay, then we can just actually, we are just giving the conditions at 2 extremity. For example, when we are talking in terms of time, then this is nothing but the value of y at initial instance, and this is the value of y at the final instant. Okay, so now we wish to apply the regular perturbation theory to solve this equation. We don't know whether it works or not, but we will give a try. Okay, so we assume the solution as y as a function of x, which will be a summation over n running from 0 to infinity yn of x times epsilon to the power n. So it will be a power series of epsilon. Okay, and then you can write, of course, expanding like this: y0 plus y1 epsilon plus y2 epsilon square up to infinity. But now again, it is a must that we know how to solve exactly the unperturbed equation, and here we know, fortunately. That's why we can proceed. So the unperturbed equation solution will be nothing but y unperturbed is equal to a cos x plus b sin x. Okay, so initial conditions give simply that y unperturbed will be sin x by sin 1, right? That is somehow easy to understand. When you don't have this term at all, but you just have these two initial conditions, you can simply see that at x is equal to 0, y is equal to 0 simply says that a is equal to 0, and then at y is equal to 1, at x is equal to 1, y is equal to 1 simply says that here it will be 1 when b the right hand side will be simply b sin 1, because a is 0. There will be no cos term, so b sin 1 will be 1, so b will be nothing but 1 by sin 1. So y unperturbed will be simply equal to b sin x, or 1 by sin 1 times sin x. Okay, so that is the case where there was exactly no perturbation. Now we put the solution. Okay, we put the solution in the power series form, of course, and we substitute this power series method in the main perturbed form of the the power series solution in this perturbed equation, and this is nothing but this d2 dx2 and the whole power series plus, so d2y dx2 plus y, so y will again be this power series itself, plus 2 epsilon dy dx, so d dx of the whole power series, that will be equal to 0. Okay, now again the same routine. You equate the coefficients of every single power of epsilon to 0, okay, and then for 0th order you will have, as expected, the unperturbed solution, unperturbed equation, that is d2y0 dx2 plus y0 is equal to 0. So it will simply be the same solution as we obtained for the unperturbed case. So y0 will always be equal to sin x by sin 1. Okay, so we agree on that. Now the coefficients of epsilon 1 gives this one, d2y1 dx2 plus y1 plus 2 dy0 dx is equal to 0. Okay, here you try to understand from this one. So the here the coefficient of epsilon 1 will be d2y1 dx2, and here it will be y1, but here already an epsilon is multiplied, so it will be dy0 dx times 2. Okay, so then this will be the equation of first order of epsilon. Okay, or for first order of epsilon. Okay, now what is this? This is nothing but d2y1 dx2 plus y1 is equal to minus 2 cos x by sin 1. So now you know what y0 is. You just do dy0 dx, which is nothing but cos x by sin 1. So it will be just minus 2 cos x by sin 1. Now minus 2 sin 1 is a constant. We just call it as a, and then the the first order equation comes d2y1 dx2 plus y1 is equal to a cos x. Okay, so this is nothing but this is equivalent to an equation which is undamped but forced with a periodic force, right? It's almost like this. If you just consider in terms of time, it will be nothing but d2y dt2 plus y is equal to a cos t. So it's a periodic force is acting, and so effectively the second order equation looks like an undamped forced equation where the force is periodic. But what is the frequency of that force? This is exactly equal to 1. Just remember this. Okay, I am coming to that next, in the next part. Okay, now note that the solution for the homogeneous part, so here this is a non-homogeneous solution because equation, because the right hand side is non-zero. So we know that for this type of thing, the total solution can be obtained by adding the solution for the homogeneous equation plus the particular solution satisfying the non-homogeneous solution equation. Okay. So the solution for the homogeneous part is known as the complementary function, and you know all that this is nothing but given simply d2y1 dx2 plus y1 is equal to 0. So this is nothing but c1 cos x plus c2 sin x, where c1 and c2 they are arbitrary constant. Okay, and the initial conditions are this. But remember one thing, directly using these initial conditions here, please do not try to evaluate C1 and C2, because you don't have the total solution for Y1 now. You can use the initial conditions only when you will have the particular solution also in hand and you have the total form. Okay, so now note that what I just said, equation 7 is similar to a forced undamped oscillatory system having its natural frequency to be equal to the forcing frequency, because here you see that omega is 1, and here also this the frequency of the force, the periodic force, is also 1, right? So this is nothing but a resonant case. Okay, so how to calculate the particular solution of that equation? So we have to search this, not, I mean, we cannot search the, the solution in the form of just proportional to cos x, but we have to search as a form of x times cos x. Okay, but if you do that and if you substitute that in this equation, you will see that your equation will come like alpha prime is equal to, so I don't know where alpha prime basically is. Okay, so alpha prime is just the, just the amplitude of this trial solution, which is not necessarily real, that is a complex quantity. So for some unknown reason I call that alpha prime. Okay, so this alpha prime is equal to minus half a cos x by sin x. Now whenever you have this type of problem, that means that you cannot really equate that cos, the coefficient of cos x on both sides, and you just have something like real e to the power ix by imaginary e to the power ix. The first message you have to understand that the trial solution should be in the form of complex quantity and not the really just only the cos x or sin x form. That's why it is better to work directly with the complex numbers. Okay, then only you can evaluate directly alpha prime more easily. Okay, so let us take now y1 px is the real part of alpha x e to the power ix. Okay, and if you now substitute this in this equation, in the main equation, perturbed equation for, the first order equation, this one, this equation, you will see that alpha will just come out to be a by 2y. Okay, and then finally your particular solution will be x times real alpha times e to the power ix. Okay, actually it should be okay, I now understand why I gave here alpha prime, because I said here it will be alpha and in this one it will be alpha prime, in order to just make a difference. Okay, here it is alpha, so alpha is 8 by 2 pi. So when this is, so the y, the particular integral for y will be x times, x is a real number, real of alpha e to the power ix. Okay, and which is nothing but a by 2, there is no i's. Okay, so this is just a by 2 x times sin x. Okay, so so you can easily see that this is because this alpha is a by 2i. So a by 2i real of e to the power ix is nothing but sin x. Okay, a times a by 2 sin x. Okay, that's exactly what we write here. And this type of treatment you have already seen in the previous lectures. Okay, so you have a particular solution of the form of some constant. Now this constant is a real constant, a by 2 x sin x. Okay, so the complete solution can now be written in the form of c1 cos x plus c2 sin x plus a by 2 x sin x. Now finally you have the right to use the initial or boundary conditions, and if you do that properly you will see, so the conditions are the same. The condition is that y is equal to 0, this is 0, y is equal to 1, this is 1. So for there is a bit subtlety that is both the y is equal to 0 is equal to 0 says that y1 is also 0. All the orders of y is 0. But y1 is equal to 1, it simply says that y0 of 1 is 1. But there is no, so if you just write y0, y is equal to y0 plus epsilon y1 everything, so except the y0, all the higher order terms would vanish at 1 as well. So for y1, both y1 at 0 and y1 at 1 should vanish. Okay, if you use that, you can easily show c1 is equal to 0. Okay, because at x is equal to 0, y1 is 0, so 0, that those two terms will vanish, so c1 is 0. And when x is equal to 1, y1 is also 0, that means that this is 0, this is 0. Okay, then c2 plus a by 2, and x is 1, so c2 plus a by 2 times sine of 1 is equal to 0. So that means that c2 will be equal to minus a by 2. Okay, and then finally replacing all the values of the constants, you finally have this, the total solution for y1 is equal to 1 by sine 1. Okay, because we also substituted the value of a over here, 1 by sine 1 sine x minus x sine x. Okay, now this was only for the y1. Okay, in this way you can also try to solve by knowing y0 and y1. You can now proceed to solve y2. Okay, good luck for you, but only with y1 you can have some good news. So you can write the total solution more, which is much more realistic than the y0. Now you will have a perturbative solution at least up to the first order of epsilon, which is not bad. So you will see the total solution will be y0 plus epsilon times y1. So it will be sine x by sine 1 plus epsilon times sine x minus x sine x by sine 1. So rearranging, you will have sine x by sine 1 times 1 plus epsilon minus epsilon x. Okay. Now the problem is that this epsilon x sine x by sine 1, okay, grows linearly with x. So if x grows as or beyond 1 by epsilon, so that is the main problem. Okay, then the perturbative part is no longer small. That will be equal to of the order of 1 or greater. Okay, so this is no longer a perturbative part at all. That is not expected, right? Okay, this type of term is in general known as secular term. Okay, now if you say that, as I said, that if we define our x variable to be varying inside 0 and 1, okay, then you can always say that the maximum value of epsilon can be very close to 1. So the total term epsilon, maximum value of epsilon times x will be very close to epsilon, not 1, sorry. Okay, epsilon, and which is of the same order of epsilon. So this will still be a valid perturbative term. Okay, so the smallness of epsilon will be retained in the term of epsilon times x. Okay, and another thing is that if this is not the case, then there is a problem, because then we cannot guarantee the smallness of this term. Okay, so only for this small or moderate value range of x, the above solution is physically meaningful. Now let's say this is not the case and x really can tend to infinity. X can actually approaches to large values, not even infinity. If it is sufficiently large, let's say your epsilon is 0.01, which we assume, let's say, for the quadratic equation in the previous part of the lecture, and we just say our x is not infinity, far from infinity, but let's say 10 to the 6, then already your epsilon is of the order of 10 to the 4. And this is, not epsilon, but epsilon times x. So this term is ridiculously bigger than this term, right? So you can see that poses the problem to the boundedness of the solution. That means it simply says, due to this one, when really x will tend to infinity, the solution will be without bound and it will really tend to infinity. Okay? But there is a problem. you can say that, well, there is no problem, maybe it has a solution of infinity. Well, now have a look at this solution, at this equation. Y double dot plus 2 epsilon y dot plus y is equal to 0. If you just multiply y dot throughout, you will have d dx of half y dot square. Here y dot means dy dx, okay, plus d dx of half y square plus 2 epsilon y dot square is equal to 0. Now our epsilon is positive, y dot square is positive, okay, epsilon is positive by definition, it's only between 0 and 1, okay. So ddx of this quantity, which is the sum of two positive definite quantities, will be less than 0. That simply says that if the initial value of this total thing, half y dot square plus half y square, which is completely reasonable, initial value is a finite value, okay, then with increasing x, basically its value is decreasing. So what can be the minimum possible value at any condition? That will be 0, because there's the sum of two squared quantities, right? So it cannot go negative, right? So there is no chance that this will go to plus infinity or minus infinity, and this is nothing but a bounded thing. So y must have a bounded solution. So if this has a bounded solution, y will be even smaller than this quantity, okay, y square will be smaller than this quantity, so y square will be again bounded and y will be then bounded, of course, so y should have always permit a bounded solution. So the solution provided by RPT can be logical only when x has a finite domain with small values. So although we started our RPT or regular perturbation theory independent of the domain of x chosen, finally we see that whether RPT will work or not, that depends on the domain of x. If it is the domain is with very small or moderate values, so that the maximum x times epsilon is at best of the order of epsilon, then we are saved, otherwise there is a problem. Now the question is that, can we improve the method to get rid of these secular terms? Okay. Well, we will try in the next lecture to address this problem. But now just to have a look that all we did here, we did in terms of a linear ordinary differential equation. First, we would have a look that how this type of secular terms also causes a problem while applying regular perturbation theory for a non-linear ODE, because non-linear ODEs will also be very, very important to discuss the context in the context of non-linear or anharmonic oscillators. Okay, so that we will first check, and then we will see that how to make some modifications in this regular perturbation method to get rid of this secular terms, and thereby we will be discussing a much more sophisticated method which is called Poincare-Lindstedt method. Okay, thank you.